Welcome to the video lecture on moments, center of mass, and centroids. Mass is defined to be the measure of a body's resistance to changes in motion. It's independent of gravity, so mass is not considered a force. But if you take a mass and you multiply by gravity, then that turns it into a weight, which is a force. So weight is mass times gravity, where gravity depends on the gravitational system that you're in. Here on Earth, the gravitational force G is equal to 9.8 meters per second squared, or 32 feet per second squared. In a more general term, you could say that any force F is a mass times an acceleration, and in this case for weight is just that mass times acceleration due to gravity. Some typical units for mass would include the slug in the US system, the kilogram in the international system, and the gram in the CGS system. And for force, in the US it's usually measured in pounds, which is a slug, times a foot per second squared. In the international system, you talk about force measured in newtons, which is a kilogram, times a meter per second squared. And in the CGS system, a dyne, which is a gram, times a centimeter per second squared. So let's start by considering a seesaw. We have on this seesaw two children, a 20 kilogram child 2 meters from the fulcrum, which is that tipping point on your seesaw, and a 30 kilogram child 3 meters to the right of that fulcrum. Now this situation is called a moment in calculus. We think of a moment of a mass m about the point P as being the mass m times the distance that mass is from point P. So that would be the mass m times x. So if we look at our seesaw over here, the left moment about this fulcrum point P would be the mass of our child on the left, which is 20 kilograms, times the distance that it is away from that fulcrum, which is 2 meters. So this would be 40 kilogram meters. The right moment would be the 30 kilogram child times his distance from the fulcrum, which is 3 meters. So this would be 90 kilogram meters. Now, in order to balance the seesaw, these two moments must be equal. And obviously, because we have a heavier child on the right that's further away, this seesaw wants to tip towards the right because it has a larger right moment. So how could I balance this seesaw and make these two moments be equal? Well, one option would be to change one of the masses. So what could I do to affect this seesaw and make it balanced by changing a mass? Well, suppose that the child on the right hand side stays 30 kilograms 3 meters away. Then that moment on that right hand side is 90. On the left hand side, if a child that's 20 kilograms hops off and a new child comes on, how heavy would that child need to be so that this will be balanced if he's still going to be 2 meters away from that fulcrum? So I'm going to keep this distance 2 meters. What would this weight, or this mass, let's call it m, need to be so that these are going to be equal? Well, on the left hand side we'd have that 2 times m divide by 2. We need a mass of 45 kilograms to make these two moments be the same. So I would need a child that's 45 kilograms to hop on the seesaw to keep this balanced. The other option is to change the distance. If the masses stay the same, I would need to shift these children left or right so that it becomes balanced. So let's say that the 20 kilogram child stays put at 2 meters away and the 30 kilogram child stays on the seesaw. How far over are they going to have to move? Let's call that x to keep these two things equal. Well, if this is 40 and this is 30, dividing by 30 means I'm going to need that larger, heavier child to be 4/3 of a meter away from that fulcrum. So he's going to have to move to the left to balance these two guys out. Okay? So let's consider these as points on a number line. You could have many different masses at many different positions, and that fulcrum is sort of that center point. The tendency of this system to rotate about that fulcrum, which we typically think of as the origin, is called the moment about the origin. So you would just take this first mass, m sub 1, times its distance from the origin, which is x sub 1, mass 2 times x sub 2, mass 3 times x sub 3, and so on, up to the very last one. Now, if this moment is 0, then we would say that the system is in equilibrium. So this seesaw is not going to tip one way or the other. If equilibrium does not occur, then there will be a center of mass. So what would we need to do to make that equilibrium be 0? Well, we're going to have to shift these masses left or right to balance this out. So to determine where that center of mass is if the equilibrium is not 0, we're going to derive sort of a formula for it. So center of mass, which is typically notated by this x bar, is the point x bar at which the fulcrum could be relocated to attain equilibrium. Now, in order to do that, you're going to have to shift these masses and these points around. So if you translate the system by x bar units, the center of mass, then each coordinate x sub I becomes x sub I minus x bar. So we're going to shift all the points either to the left or to the right by this amount x bar. After shifting, this system should now be in equilibrium so that its moment about the origin is going to be 0. So what does that tell us? Well, the moment about the origin is defined to be those masses times their distances from that fulcrum. So our masses are these m sub i's, and our distances from the fulcrum after we've translated them are these. So these would be our distances, and I'm going to sum up all of those masses and all of those distances from 1 to n. And since we're now in equilibrium because we've shifted the system over, this would have to equal to 0. So if we distribute our m sub I across, we get m sub I x sub I minus m sub I x bar. And what I'm going to do now is I'm going to separate this sum into two different sums. So the sum of the m sub I x sub i's minus the sum of the m sub I x bar. And since this is set equal to 0, or equal to 0 because we're in equilibrium, let's just go ahead and add this sum over to the right-hand side. And this x bar is a constant. It's independent of I. So you can think of pulling that x bar out. So this is like x bar times the sum from 1 to n of m sub I. So in order to find out what this x bar needs to be, we can solve this equation by dividing both sides by this sum of these m sub i's. So we get a formula. X bar is now defined to be all of this right here, the sum from 1 to n of our masses times our positions over the sum of all of our masses. So this top one right here is actually our moment of the system about the origin. So this is the m sub 0, the moment of all of our points from the origin originally. And what we're doing is we're dividing that by the total mass of our system. So when we do that, we get our center of mass, where that equilibrium point needs to be. So here it is summarized. If you have the point masses m sub 1, m sub 2, m sub 3, all the way up to m sub n, located at x1, x2, x3 through x sub n, then the moment about the origin, m sub 0, are each of these masses times their corresponding positions. So m1, x1 plus m2, x2, and so on. The center of mass is x bar, and it's equal to this moment about the origin divided by m, where m is the sum of all of the masses. So it's the total mass of the system. So here's an example. Suppose that we want to find the center of mass of the following point masses lying on the x-axis. So we've got mass 1 is 7, mass 2 is 4, mass 3 is 3, mass 4 is 8. Position 1 is -3, position 2 -2, position 3 is 5, and position 4 is 6. So if you want to visualize this on a number line, you could just draw your number line, and these positions, these x's, are going to tell you where these masses lie. So here's the origin, and my first position is at -3, and that's mass 1, which is 7. And then at -2, we have mass 2, which was 4. And then at 5, we have mass 3, which was 3. And then at 6, we have mass 4, which was 8. Okay, so we're measuring from the origin. That's going to be our fulcrum. So in order to find the center of mass of this system, we're going to use our formula that x bar is the moment about the origin over our total masses, or in other words, the sum from 1 to, in this case, 4, since we have 4 of these guys, m sub I times x sub I, so their masses times their positions, over the sum of all the masses. So written out, without using this summation notation, since I only have 4 points, it's not necessary to get so fancy as with this summation. Let's just take our first mass times its first position. So the mass is 7, and its position is -3, away from the origin. So that's mass 1. Mass 2 has a mass of 4, and its position is -2, away from the origin. Mass 3 has a mass of 3, and its position is 5 units away from the origin. And mass 4 has a mass of 8, and it's 6 units away from the origin. So that's what I mean by m sub 0. Those are your masses times your positions. And we're going to add all of that up, and at the same time on the bottom we're going to divide by our total mass. So all 4 of these masses added up. So the numerator, when you go ahead and add that, that's going to give you -21 minus 8 plus 15 plus 48, and on the bottom you're going to get 22. So this is going to be 34 over 22, or 17/11, which is about 1.54. So if you look at our number line up here, here's 1, so 1.54 would be right about here. So you can imagine your little seesaw. That would be the point where the center of mass would be, where you would have equilibrium. If you shifted that fulcrum over and positioned it right here, then this seesaw would be balanced. So that's what the center of mass represents, and we would just say that x bar is 17/11. Okay? So what do you do if you have a two-dimensional system instead of just a one-dimensional system? So in a two-dimensional system, you're still going to have these masses, but now they're going to have x and y coordinates. So now we're going to have to define a moment about the x-axis and a moment about the y-axis. So if these are my 3 masses here, my moments about the x-axis are going to be the masses times their positions away from the x-axis. So that would be this distance away from the x-axis, which corresponds to this y-coordinate, this distance away from the x-axis, which is this y-coordinate, and this distance away, which is this y-coordinate. And then if you have your moment about the y-axis, you would take your mass times the distance away from the y-axis, which would be this distance here, which is your x value, this distance here, which is your x value, and this distance here, which is your x value. So we're going to define an m sub x and an m sub y. So moments in center of mass for a two-dimensional system. Let your point masses be m1, m2, m3 up to m sub n, located at x1, y1, x2, y2, etc. Then the moment about the y-axis, which we're going to call m sub y, is actually m sub 1 x1 plus m sub 2 x2 all the way up to m sub n xn. So keep in mind here that we're finding the moment about the y-axis, but we're actually using the x coordinates. And the reason for that is from our picture that we just looked at up here. The distance away from the y-axis is actually the x coordinate. So that's why we're using the x's when we find the moment about the y-axis. Similarly, the moment about the x-axis is going to be m sub x, and it'll be m1y1 plus m2y2 up through m sub n y sub n. And this one uses the y coordinates, and that's because the distance that these masses are from the x-axis is going to be their heights, which are these y values. So the center of mass of the system, or the center of gravity, is called x bar comma y bar, and x bar is going to be the moment about the y-axis, so that's the one using all these x's here, divided by the total mass, and y bar is going to be the moment about the x-axis, which is the one that uses all these y coordinates, over the total mass. Okay, so for example, suppose that I have three masses, 2, 3, and 4, at these three locations. So let's draw that picture for a moment. We have -1, comma -2, and that's our first mass of 2. Then we have one at 1, comma 3, and that's a mass of 3. And then we have one at 0, comma 5, and that has a mass of 4. So these are our three different positions. So to find the center of mass, we're going to be using this formula right here. And to find our x bar, we're actually going to be using the moments about the y-axis over our total mass. So the moments about the y-axis use the x coordinates. So we're going to take each of these x coordinates times the corresponding mass, and that's what m sub y is. So -1 times the mass 2 plus 1 times the mass 3 plus 0 times the mass 4, and we're going to divide all of that by the whole mass of the whole system, which is this 2 plus 3 plus 4. So that's going to give me -2 plus 3 plus 0 over 9, which is just 1/9. So then for y bar, we're going to take the moment about the x-axis over our total mass. So now we're going to use all of these y coordinates, because that gives me my distance away from the x-axis. So -2, and that had a mass of 2, +3, and that had a mass of 3, and +5, and that had a mass of 4, over the whole mass, which was 2 plus 3 plus 4. So this is going to give me -4 plus 9 plus 20 over that 9, which is going to give me 25/9. So my center of mass, x bar, y bar, is going to be 1/9 for the x value and 25/9 for the y value. So the position of that would be just a little bit past 0, 1/9, something really small, and then 25/9 is about 2.7. So this would be somewhere about here. Oops, I did it a little bit too low. So about 2.7. So somewhere up here would be your center of mass. Okay? All right, now we're going to make things a little bit more complicated. We're going to talk next about something called a planar lamina, which is a thin, flat plate of material of constant density. So imagine a really thin sheet of metal, for example. So here's a circular shape or a parallelogram type shape. It's a very thin, flat piece, really has no depth to it or thickness to it, and it's just a plate of constant density. Now normally when we talk about density, density is defined to be mass divided by volume, but for a planar lamina, density is mass divided by area, because this doesn't really have any thickness to it. And we define that to be rho. That's this fancy Greek letter P right here. So consider having an irregularly shaped planar lamina. So not a nice circle or a nice rectangle. Suppose it's got a weird shape, bounded by some function f and some function g between a and b. So here's my planar lamina right here. F's on top, G's on the bottom, and it's between A and B. So this irregularly shaped planar lamina. Now the mass of this sheet right here would be its density, which is what we're calling our rho right here, the mass per area, times the area. Okay, if you look at this formula right here, mass is going to equal this density times this area. So in order to get the mass of this planar lamina, we're going to take its density, which is what we're calling our rho, times its area, and the area of this irregularly shaped region could be found using an integral in calculus. So the area of this shape is going to be the integral from A to B. The top curve is f of x, so we want to use that first and do f of x minus g of x dx. So there's our density times our area, and that is now our mass. Now to find the center of mass of this lamina, what we're going to do is we're going to partition it and take this interval A to B and partition that whole interval into n equal width subintervals. So here's a little slice right here in black. So the mass of that ith rectangle is going to be its density, which again is our rho, times the area of that little slice. So the density is our rho, and our area is going to be the area of this rectangle, which is its height times its width. Now its height is this top function's y value minus the bottom function's y value. That would be that vertical distance. So we could write that as f of x sub I minus g of x sub I. So that vertical height right there is just the top function minus the bottom function at x sub I. So this is like our height, and we're going to multiply that by our width, which we're just going to call delta x. So when we do our partition, each of these little rectangles is going to have a nice equally spaced subinterval, so delta x will be that width. So we've got our density times our height times our width, which is our area. So the mass of this little stripe is going to be given by this formula. Now, what would be the distance of that away from the x-axis? Remember, to find a center of mass, you need a mass times a distance. Now, we've just figured out what the mass is going to be. Now we need to figure out what the directed distance is going to be from the x-axis. So if you think about this slice, there's a point right in the middle, right here, that is going to represent sort of the center of that slice, and we want to know how far that point is away from the x-axis. Okay, so I'm going to call that center point x sub I comma y sub I. So the height that it is away from the x-axis is this y coordinate right here. Okay, so the directed distance that this slice is from the x-axis is just going to be given by that y sub I. Now, how could we calculate what that center point is? Well, it's determined by this top point and this bottom point down here, which are our f of x sub I and our g of x sub I. And what you'll notice is that center point right there is the average of these two top and bottom points. And how do you find an average in mathematics? You add them up and you divide by 2. So the definition or the formula for this y sub I, this center height, is just the f of x sub I top point plus the bottom point g of x sub I divided by 2. It's just the average of the top and the bottom endpoints. Okay, so it's sort of that midpoint of the y values. So how do we get the moment then of this system about the x-axis? Well, we're going to take the mass of our rectangle times its distance from the x-axis. That's what a moment is. It's a mass times a distance. So if I do that here, then this is going to be, and this again is about the x-axis, is going to be my mass, which is given by all of this, the density times the height times the width. So there's our density times our area. And then that's our mass. That's this part of our formula. Now we need to take all of that times our distance that this mass is away from the x-axis, and that was this formula right here, this midpoint. Now that's just the moment about the x-axis for that particular rectangle. Then what we would have to do is sum up all of these different moments for each of those rectangles, and as we make those rectangles get skinnier and skinnier so that this delta x goes to 0, what do you think this is going to turn into? It's going to turn into an integral. So this is going to turn into the integral rho. I'm going to pull that rho out front from a to b of f of x minus g of x, that's from this part right here, times f of x plus g of x all over 2, that's from this part right here, and the delta x turns into a dx. So this is going to be our formula for the moment about the x-axis when we have an irregular planar lamina shape. Okay? All right, now that's just the moment about the x-axis. What about the moment about the y-axis? So what would m sub y be? Well, the good news is the mass is the same, okay? This mass right here is going to be the same formula that we've already figured out. So that'll be our rho times our height, which is the f of x sub I minus g of x sub I, times delta x, which was our width. And then what we're going to need to do is figure out what the distance is of this rectangle from the y-axis. So let's look at our picture again. If this is my rectangle, how far away is this rectangle from the y-axis? Well, that's this x-coordinate of this point right here. So that's this x sub I. So the directed distance from the y-axis is just going to be x sub I. So again, this is just the moment about the y-axis of that particular rectangle. So if I take a limit and I let these rectangles get smaller and smaller and I let delta x go to 0, then this turns into an integral. And the moment about the y-axis becomes rho times the integral from a to b of f of x minus g of x, that comes from right here, times x, I'm going to put the x in front, and that comes from here, and then the delta x turns into my dx. So these are where the formulas are derived from, and formally this is what they're going to look like. Okay, so the moments and center of mass of a planar lamina. Let's let f of x be the higher function, the greater function. So f is greater than or equal to g on an interval a to b, and let the planar lamina have uniform density rho. Then the moments about the x and the y-axis are given by these two formulas. Remember that for the moment about the x-axis, this is the one that uses that midpoint right here. And that's because this center point is just the midpoint of this top point and this bottom point. And we're trying to measure the distance from the x-axis. So we take the average of these two. So that's where that's coming from. And then right here is just your area. This is coming from your area. For the moment about the y-axis, you also need that area, but your directed distance from the y-axis is just this x-coordinate of this point. So that's where that x comes from. And your area times your rho is what gives you your mass. So that's why the rho is in there as well. So these are called the moments. Then to get the center of mass of the entire planar lamina, you take those moments and you divide them by the total mass. And in this case, that's just going to be your area, which is this area integral from a to b of f of x minus g of x times your density rho. So if you rewrite these formulas, then x bar is going to be the moment of y over m, and that's going to be all of this, so rho times the integral from a to b of x times f of x minus g of x dx, all over the total mass, which is our density times our area. And then for the y bar, the center of mass y coordinate, that's going to be the moment about the x-axis divided by m. So that's this height right here, and that's the one that uses the average of the upper and the lower functions. So this is going to be rho times the integral from a to b of the average of the two, add them up, divide by 2, times the difference, all divided by the total mass, which is your density times your area. Now what you'll notice here is since we're using that density rho on the top for those moments and on the bottom for those total masses, they actually end up canceling out on the top and the bottom. So you'll notice that the density will be in both the numerator and denominator of the center of mass, so it will cancel out. And so the center of mass of a lamina of uniform density depends only on the shape of the lamina and not on its density. So for this reason, the point x bar y bar is sometimes called the center of mass of a region or just the centroid of the region. And to find this centroid, just to make our lives easier, we just assume that it has constant density and we let this rho equal to 1. And that gives us one less thing that we have to worry about. So in general, if you let your rho be 1, then those same formulas that we used up here still apply, but you're just not going to have that rho in front. So your total mass is actually just going to be your area because you don't have to multiply by your rho, which would just be 1. And your x bar is going to be this x times f of x minus g of x all over that total area. And your y bar will be that average times f of x minus g of x all divided by your total area. You can also do this going sideways. If you have functions that are defined as x in terms of y, these same formulas apply, but just with y's thrown in. And we'll see an example of that in just a moment. So this probably looks like a totally different language when you first see it. There's a lot of formulas involved, but they're actually pretty simple to use once you get the hang of it. So let's try some problems. Find the centroid of a region bounded by y equals square root of x, comma y equals 0, and x equals to 9. So when it asks you to find the centroid, and it uses that word centroid, then that means you can assume that your density, your rho, is going to just be 1. So we don't need to use the rho at all. So let's first visualize our region here. We have the square root of x, we've got y equals 0, and we've got x equals 9. So this is our region. And we want to find its centroid, which is its center of mass. So somewhere in here, there's a point where that mass is sort of centralized, right? So how do we find the coordinates of that point? Well, the first thing we're always going to start off with is finding the total mass. And in the case of a centroid where your density is 1, that's the same thing as just finding the area of this region. So let's find the area of this region right here. And that's just using a good old integral. We're going to take the top curve, which is our square root, and we're going to subtract the bottom curve, which is just 0. And our bounds for x are from 0 to 9. So this is just the integral of x to the 1/2, which becomes 2/3 x to the 3/2 from 0 to 9. And when you plug in 9, you're going to get 2/3 9 to the 3/2. When you plug in 0, you're just going to get 0. Square root of 9 is 3. 3 cubed is 27. 27 divided by 3 is 9. 9 times 2 will be 18. So this area is 18 units. So now what we're going to do, once we've found that area, remember our formula up here, that's this A, we need to find x bar and y bar by finding these integrals here. So we're going to find our moment about x and our moment about y. And when I divide both of these by a, that's going to give me my x bar and my y bar. Okay? Now the moment about x, which formula is this that we use? Well, think about it for a moment. If we're taking the distance away or up to that x-axis, the moment about the x-axis. That means we want this vertical distance here. So if you imagine a little slice, remember that that height of that point comes from this top and this bottom averaged together. So that's going to be the formula, or that integral formula, that uses the average. So our bounds are still 0 to 9, and what we want is the top function, which was square root of x, plus the bottom function, which was just 0, divided by 2. And then we need to multiply this by the height of this slice, which is the top function minus the bottom function, times the thickness of that slice, which is our dx. So there's our area right there, times our directed distance away from the x-axis. So this is the integral formula that we want to use. For the moment about the y-axis, that's going to use this directed distance here. So our integral bounds will still be 0 to 9, but this distance here just corresponds to the x value of that point. So we're just going to call that x. And we have to multiply that distance times our mass, which comes from our area, the top function, minus the bottom function, which is your height, times your width. Okay, so these parts of the formulas will be the same for both m sub x and m sub y. The only part that's different is here we use the average when we want that y coordinate, and here we just use x when we want that x coordinate. Now we actually need to evaluate these two integrals. So for this first one, I'm going to take that 1/2 and I'm going to pull it out. And since this goes to 0 and this goes to 0, that's just a square root of x times a square root of x, which is just x. So when I integrate that, that's going to give me x squared over 2 from 0 to 9. So that's 1/4 of 9 squared minus 0 squared. 9 squared is 81, so this will be 81/4. Okay, then for the second integral, this is 0, so x times square root of x is x to the 3/2. And when I integrate that and add 1 to the power, it becomes 5/2 with the 2/5 out front. So when I plug in 9, I'm going to get 2/5 of 9 to the 5/2 minus 0 to the 5/2, which is just 0. Square root of 9 is 3, and then this is going to be 3 to the 5th times 2, all divided by 5, which becomes 486 over 5. Now we're not done yet, okay? These are just the moments. To get the center of mass, or the centroid, you want your x bar and your y bar. Now x bar is the moment about the y-axis. Think about why we're doing that, because the moment about the y-axis is using these x coordinates. So we're actually going to use this number divided by our area. So our moment about the y-axis, we came up with that 486 divided by 5, and we want to divide that by our area, which we found earlier was 18. So if you reduce that, that's about 5.4. Then for your y bar, you're going to use the moment about the x-axis over your area. And you're using the moment about the x-axis because that's the distance from the x-axis, which is really your height, your y. Okay, so that's why it's going to give me y bar. So my moment about the x-axis was this 81 over 4, and our area again was 18. So when I simplify that, that's 1.125. So there's my y bar. So my center of mass is 5.4 for the x and 1.125 for the y. And just to double check and visualize that that looks about right, we've got 5.4, would be somewhere right around here, and then this is only going as high as 3 up here, so 1 looks like it would be right about there. So where I had my first dot was right about where that center of mass ended up being. So that point right there is 5.4, comma 1.125. Okay, let's try another one. Again, the formulas on these are a bit overwhelming, so it just takes some practice knowing how to use them. But after you know how to set them up, the actual calculus involved is pretty straightforward. But you have to know what goes where. Okay, so here we want to find the centroid of a region bounded by y equals x squared and x plus y is equal to 2. So if we draw a picture of this, x squared is just a parabola, and x plus y equals to 2 is just a line that goes through 2 on the x-axis and 2 on the y-axis. So it's going to look something like this. Okay, so our region bounded is this region right here. Okay. All right, so if we take a look at this piece, we want to find its centroid. Again, when it says centroid, that lets you assume that your density, your rho, is equal to 1. So it just gives you one less piece of that formula that you have to worry about. So step one is always to find the original area of this region. Now, if you did have a linear density, a density rho, then you would just take this area that we're going to find and you would multiply it by that rho. When we're finding a centroid, we just get to assume that that rho is 1, so it's not going to change this area at all. So the area of this shape would just be the top curve, which is our line, down to our bottom curve, which is the quadratic. And if I do my vertical slice like this, that's going to intersect that x-axis. So I'm going to use x variables here. So what would be the equation of this line using x's? Well, this is y equals 2 minus x. So I want the 2 minus x coming first because it's on top, minus the x squared on the bottom. And then what are my bounds? Well, we're going to need to either use a calculator to figure that out, or we're just going to need to do a little bit of algebra. So to figure it out, you're just finding when this y value here is equal to this y value here. So if I set my two curves equal to each other, I get a quadratic equation which factors, and we get x plus 2, x minus 1, so negative 2 and positive 1. So those are going to be my bounds. So when I integrate here, I'm going to get 2x minus x squared over 2 minus x cubed over 3 from negative 2 to 1, and I'll let you do the algebra there to plug that in, but you get 4.5. Okay, so there's our area. That's what we're going to divide our moments by to get our x bar and our y bar. So then the next thing we need to find is the moment about the x-axis and then the moment about the y-axis. Okay, so the moment about the x-axis is going to be the integral, again, from negative 2 to 1 of, and then you have to decide which formula you're going to use. About the x-axis is this distance here. If you imagine the center of that slice, that's this vertical distance, which is going to come from the midpoint of this point on top and this point on the bottom. So we're going to use that average formula. We're going to take the top curve, which was the 2 minus x, and we're going to add to it the bottom curve, and we're going to divide that by 2. So that'll give me the height of the midpoint in the middle. And then we need to multiply this by the top curve minus the bottom curve. And that just comes from that area again, that height times that width. So that's the formula for the moment about the x-axis. The formula for the moment about the y-axis will be very similar. It will also have that 2 minus x squared dx, doing the top curve minus the bottom curve. But now the distance that this center point is from the y-axis is just that x coordinate. So this just uses an x instead of this big midpoint formula. So those are my two different integrals. Now we just have to simplify them and solve them. So for the moment about the x, let's go ahead and take that 1/2 and pull it out. So we're going to get 2 minus x plus x squared times 2 minus x squared dx. And you can certainly FOIL all of this out. It's not hard to do, it's just tedious. So I would probably, on a problem like this, since I know that you could do it, I would let you just use that function integrate command on your calculator and show that this is just 7.2. Okay? Likewise over here, if I go ahead and distribute, this one's easier to go ahead and distribute, you'd get 2x minus x squared minus x cubed. And this one is fairly easy to integrate. You're just going to get an x squared minus x cubed over 3 minus x to the 4th over 4, and then you would plug in your bounds. So the moment about y, when you plug in those bounds and subtract, is negative 2.25. Now we're not done yet, because we have to take these moments and we have to divide them by this area that we found earlier. So x bar is the moment about the y-axis over that area. So this number right here divided by that 4.5 area that we got, and that gives me negative 0.5. Y bar is the moment about the x-axis divided by your area. So that was this 7.2 divided by our 4.5 area, and that's 1.6. So my centroid, or my center of mass, is going to be at negative 0.5, or negative a half, comma 1.6. And again, that's right about where I drew that first little dot. Okay, at about negative a half, comma 1.6. So it looks about right. Okay. All right, another example that asks us to find the centroid. We want to find the centroid of the region bounded by x equals 9 minus y squared and x plus y equals to 3. Now this one's a little bit trickier in one respect, because our function here, x equals 9 minus y squared, is x as a function of y. So this is going to be one of these sideways parabolas. So it makes it a little bit difficult. And instead of using our normal formulas, let me back up here for a moment to our formula page. We're actually going to be using these formulas down here when we're going sideways and using dy integrals instead of dx integrals. Okay, so let's see how that changes things. First, let's draw a picture of what we're talking about. Now 9 minus y squared, that's a sideways parabola. It's got a point to the left because of the negative in front of the y squared. And if y is 0, that makes x equal to 9. So I know that this is going to hit at 9 on the x-axis. And if y is 3 or minus 3, then that makes x 0. So this has intercepts on the y-axis at negative 3 and positive 3. So my sideways parabola is going to look like that. And then x plus y equals to 3 hits the y-axis at 3 and the x-axis at 3. So this is a line that looks like that. So our region is right here. Okay, so let me take away some of these other pieces. All right, so here's my region. We want the centroid of that. So again, we get to assume that our rho, our density, is 1. And our first place to start, always, is to find our area. Now on this problem, you wouldn't want to take a vertical slice, because if you do a vertical slice over here, on the top will be the parabola, on the bottom would be the line. But if you come over here and you draw a vertical slice, on top would be the parabola and on the bottom would be the parabola. So that would require two different integrals. So to make our life easier, we want to take a sideways slice, so that no matter where you draw that sideways slice, you can see that on the right you're always on the parabola, and on the left you're always on the line. And that way we're consistent, which means we only need one integral. Now, to do this sideways integral means we're going to have to use y variables, because this slice is going horizontally. So what is the equation of this parabola in terms of y? Well, that's what I have right here. We always want to do right minus left. So here's the right curve, minus the left curve, which is this line. So now I want to know what this line is in terms of y's. So we need to solve this for x in terms of y. So that would be 3 minus y, and that's what I'm going to subtract from my parabola. So here's right minus left dy. We also need to know our bounds. So if we take this x and set them equal to each other, we'll be able to find those intersection points. So I'm going to get a 0. I'm going to get y squared minus y minus 6. And when I factor this, we get y minus 3, y plus 2. So y has intercepts at negative 2 and positive 3. So this is negative 2 up to 3. And those are going to be my bounds. So this integral is just 9 minus y squared minus 3 plus y when I distribute my negative. And combining a few like terms here, we're going to get 6 minus y squared plus y dy. So that's going to integrate into 6y minus y cubed over 3 plus y squared over 2 from negative 2 to 3. And I'll leave that for you to plug in. You get 125 over 6. So there's our area. That's what you're going to divide your moments by to get your center of masses. All right, let's find our moments. So we need the moment about the x-axis and the moment about the y-axis. So we have to be a little bit careful here because we're going sideways. So let's look at our picture for a moment. If we want the moment about the x-axis, then that's going to be the distance that this point is right in the middle here from the x-axis, which just so happens to be the height of that point. If you think of this point right here as some x comma y, then the height of that point is your distance away from the x-axis. So that's just going to be y. So in our integral formula over here, we're going to take that y times our area, which was the right curve minus the left curve. So this 9 minus y squared minus 3 minus y. The curve, the parabola minus the line. And our bounds again were negative 2 to 3. Now in the two previous problems, when we were finding the moment about the x-axis, we used the average or the midpoint right here. And this is switched because we're going sideways. So the moment about x and the moment about y have formulas that are kind of opposites now because we're going side to side. Okay, so the moment about y then, what would its integral look like? Well, that needs to know what this horizontal distance is, which is this x value right here, but unfortunately we're not doing an x integral anymore. So that's why I can't just use an x in my formula. Now I need to figure out what x is. And if you think about x here, this little dot right here, that x is this right endpoint and this left endpoint. The average of those two, or the midpoint of those two, is that x right there. So if we add up the left plus the right and divide it by 2, that'll tell me what that midpoint x needs to be. So that means in my integral formula, we're going to take our left point, which is the parabola, plus the right point, which is the line, and we're going to add them up and divide by 2. So that gives me the position of that x coordinate. And then we always multiply this by our area, which is our left curve minus our right curve times dy. So in the last two examples, these two expressions were switched when we were using x integrals. When we use y integrals, they get swapped. Okay? So now if we try to clean these up a little bit, I won't integrate it all out, but just to clean it up a tad, remember that you want to distribute your negative here and clean it up. So we're going to have that 6 minus y squared plus y right here times that y. So this is 6y minus y cubed plus y squared. So that would give you y squared times 3 minus y to the 4th over 4 plus y cubed over 3, and then you would plug in your bounds. And that gives you 125 over 12. Then if we go ahead and clean up this integral for the moment about y, this is going to be again that 1/2 that could get pulled out from -2 to 3. 9 plus 3 is 12 minus y squared minus y. And then inside of here, that's going to simplify to that 6 minus y squared plus y. And that one is too tedious for me to FOIL out and clean it up and integrate. So you can use your calculator for that. And when you do that on your calculator, you get 625 over 6. So to get the actual centroid, we want x bar, which is going to be the moment about y over our area. So that's this 625 over 6 divided by our area, which was 125 divided by 6. The 6's cancel, and 625 divided by 125 is 5. And then y bar is going to be the moment about x divided by our area, which was 125 divided by 12 over our area, which was 125 over 6. The 125's cancel, and when I multiply by the reciprocal, I get 6/12 or 1/2. So my centroid is x bar comma y bar, which is 5 comma 1/2. And just to visualize that, that looks about right, because that's going to be just about where my little black dot is, right here in the middle. Okay? All right. The next example is a little bit different. This one gives you this shape here, this simple plane region, and we want to introduce a coordinate system and then find the centroid of this region. So what we're going to do first is decide where we want to place this, and how you place it on your coordinate system makes a difference in what your final answer is going to be. So the answers will vary depending on how you set it up. So what I'm going to do to make the most sense is I'm just going to let this be my y-axis, and I'm going to let this be my x-axis. And what we're going to do here when we get this sort of shape here is we're going to chop it up into simpler shapes that would be fairly easy to find the centroid of if you just had that one shape by itself. So the easiest way to chop this up is to maybe put a chop right here. This is over at 1. Put a chop right here, and we get 3 different rectangles. Now what we can do then is it's easy enough to sort of eyeball these 3 different rectangles and find the centroid of these 3 rectangles. So we're going to find the centroid of each of the 3 rectangles. And you should be able to just see what it is. If your width of this first rectangle is 1, then your centroid is going to be halfway in between. So the x-coordinate is going to be a half, and the height of this rectangle is 3, so half of 3 would be 1.5. So the centroid right here in the middle is going to be 1/2 for the x and 3/2 for the y. Now for this next one, if this is at 1 and this whole length is 3, then we're over at 4 here. So this is 1, 2, 3, 4. So where would that center point want to be? My little marks here are not quite equally spaced. But you can see that between 1 and 4, the average of that 1 plus 4 is 5 divided by 2 would be 5/2. So this is right at 5/2 for the x, or 2.5. And then what would be the average height here? Well, the whole height is 1, so the midpoint height would be 1/2. So this dot right here must have a y-coordinate of 1/2. And then this last shape over here is actually a square, so its center is going to be right in the middle, and that means that the x-coordinate is going to have to be right at 5, halfway between 4 and 6, and the height is going to be halfway up this height of 2, which would make it a height of 1. So for these simple shapes, you can just eyeball where that centroid would be. Now to get the centroid of the entire region altogether, we're going to need to consider areas as well, and that's what we've been doing in the last few examples. We always took those moments and divided by the areas. So let's find the area of our three different regions as well. So our area of the region will just be the area of each of our three rectangles. And this first rectangle is 1 by 3. So its area would just be 3. The second rectangle is 3 by 1. So its area will also be 3. And the last one is just a square, 2 by 2. So its area would be 4. So that makes the area of the entire region, 6 plus 4 is 10. So to get your x bar of the entire region, what we're going to take is the x values of each of our three centroids, and we're going to sort of weight them by the area of that particular shape. So we're going to take this 1/2 and we're going to multiply it by the corresponding area of that particular rectangle. And then we're going to do that for the middle one and for the right one as well. So our first x value is 1/2. And the area of that rectangle was 3, this first one right here. The middle rectangle has an x value of 5/2, and its area was also 3. And then the last square had an x value of 5, and its area was 4. So when you multiply all this together, we're going to get 3/2 plus 15/2 plus 20, so that's going to be 18/2 or 9, plus 20 is 29. And what we need to do with this, we're not quite done yet, is we need to take all of those moments times, or the moments, which are the distances times the masses, and we need to divide all of these by that total mass, which in this case is that total area. So we need to take this 29 and we need to divide by that area. So our final x bar will be 2.9. Okay, so let's repeat that process for y bar. Y bar is going to do the same thing. It's going to take the y coordinates of all three of these points, and it's going to multiply each of those by its corresponding area. We're going to add all that up, and then we're going to divide by the total area. So our moment is going to be that first y value, which was 3/2, times the first area, which was 3, plus the second y value, which was 1/2, times the area, which was 3, plus the third y value, which was 1, times the area, which was 4, and we're going to divide all of that by that total area, which was 10. So we get 9/2 plus 3/2, which is 12/2, or 6, and 6 plus 4 is 10, so this is 10 over 10, or just 1. So the center of mass is going to be 2.9, 1, and if you look at your picture up here, that would be, right about almost where that dot is right there, just shifted over a little bit to the right a smidge. Okay? And notice that the centroid that we ended up with, 2.9, 1, it was not the averages of these three different centroids that we got earlier. So you do need to sort of weight, if you will, these x and y coordinates with the corresponding areas of those shapes. Okay, the last thing that we're going to talk about is just a simple theorem called the theorem of Pappus. And what it says is if you have a region R in a plane and L is a line in the same plane such that this line does not intersect the interior of our region R, then if little r is the distance between the centroid of our region and the line, then the volume of the solid of revolution formed by revolving r about this line is given by the formula 2 pi r times a, where a is the area of your region. So this Pappus theorem basically gives us a quick, easy way for calculating a volume of revolution. Otherwise, we'd have to do that whole disk, washer, or shell method, which is pretty time consuming. So if we know what the centroid is of our region and we can visualize this picture that's going on, then this is a really nice, quick, easy formula to use. So here's an example. Use the theorem of Pappus to find the volume of a 2-foot by 4-foot rectangle revolved about a line 3 feet to the right of the longer boundary. So the first thing that you need to do here is draw yourself a picture and again set up a coordinate system for yourself. So I'm going to draw my axes, and on these axes I'm going to draw a 2-foot by 4-foot rectangle, and you can place it wherever you like. I'm just going to position it like this. So this is 2 and this is 4. And then what we have is a line that's 3 feet to the right of this longer boundary. So 3 feet to the right would put it at 5. And what we're going to do is we're going to rotate this rectangle around our line, so you can kind of visualize what it would look like if you had circles around the tops and the bottoms. Okay, now to avoid having to use the disc, the washer, or the shell method, let's use theorem of Pappus if we can. In order to use it, this volume is going to be given by 2 pi r times a. Now, finding the area of this rectangle, that's easy to do. I already know that that's 8. So that part of this is simple. The only part that might be tricky is finding this r. Now, r is going to be the distance between the centroid of this rectangle and the line. Now, because this is a nice rectangle, it should be easy for us to figure out where that centroid is going to be. It's going to be right in the center. And r is going to be this horizontal distance going across. So what are the coordinates of this centroid? Well, it's going to be the midpoint along the bottom. So if this is from 0 to 2, then that centroid needs to be at a position of 1 along the x-axis. And it's going to be along the midpoint on the y-axis as well, which is going from 0 to 4, so the midpoint would be at 2. So that centroid must be at 1, 2, based on how I set it up in my coordinate system. So if I know that centroid, how far away is that centroid from my line? Well, this is a unit of 1 and this is a unit of 3, so that makes this radius 4 units. So I do know r, which means 2 times 4 is 8, 8 times 8 is 64, so this volume is just 64 pi. And I didn't have to draw any discs, washers, or shells to find that volume. So it's a really quick, easy way to find a volume, assuming that you can find the centroid. Okay? All right. Lots of complicated formulas in this lecture. They're fairly easy to use once you get them set up correctly, but it's a lot to kind of get through. So practice as much as you can. Good luck.